Hello, students. So, I hope you are doing good. So, today we are going to discuss next chapter, electromagnetic waves, NCRT section 8.1 to 8.2. So, this is the disclaimer. Strategy for comparative exam for this chapter, electromagnetic waves. So, you have to understand Maxwell's equation and their significance. Learn the complete electromagnetic spectrum, radio waves to gamma rays. You may have discussed or learned this electromagnetic spectrum in chemistry also. Okay. Practice numerical problems involving energy and momentum of EM waves. Focus on questions related to propagation of electromagnetic waves in different media. And please visit https://forum.pruter.ai for book recommendations and guidance. So, what are the learning objectives? So, after this lecture, you will be able to understand the concept of displacement current, which we are going to discuss in detail, and explain how Maxwell modified Ampere's law. Okay, so we have discussed Ampere's circular law in moving charges and magnetism. So, what was the limitation of Ampere's law and how Maxwell modified that law by identifying the inconsistency in it and adding the displacement current term to make it logically consistent. Index of topics that we are going to discuss today is NCRT section 8.1 introduction and NCRT section 8.2 displacement current. Okay, so let's start with the introduction 8.1. So from Faraday's law, we have discussed Faraday's law in electromagnetic induction. So there we have discussed that according to Faraday law, EMF induced is equal to d phi b upon dt, means rate of change of magnetic flux with respect to time. Okay, and we have taken only magnitude. In Faraday's law, Faraday only given the magnitude of EMF induced. Okay, and direction or polarity of EMF induced was given by Lenz's law, and collectively it was called Faraday's Lenz law. That was epsilon equal to minus d phi b upon dt. Okay, but only Faraday's law is epsilon, or we can say magnitude of EMF is equal to rate of change of magnetic flux, and it can be inferred that time varying magnetic fields from that law. What we can infer, that time varying magnetic field produces an electric field. Okay, so in that Faraday's law, we have discussed that how we move the magnet towards the coil. We have discussed about three experiment of Faraday and Henry. Okay, in one experiment there was a coil and there was a magnet, and there was a relative motion between magnet and coil, due to which magnetic field uh, lines that were passing through the coil changes and magnetic flux was changing through the coil, due to which electric field, or we can say EMF, is induced. Okay, and that is called time varying magnetic field, that we are moving the magnet and there was a relative motion between magnet and coil, and due to which magnetic field lines passing through the coil was changing. That means time varying magnetic field was being produced, due to which EMF was induced in the coil. That was given by Faraday law of induction. Okay, so this law inferred that time varying magnetic field produces electric field. Now a key question arises, that does the reverse effect exist? Does a time varying electric field produce magnetic fields? Okay, but we know that electric field, or we can say moving charges or current flowing through the wire, produces magnetic field. But can time varying electric field produce the magnetic field? Okay, that was the question. Like time varying magnetic field produce the electric field. Okay, so is this reverse effect exist? So James Clerk Maxwell argued that this is indeed the case. Not only an electric current, but also a time varying electric field generates the magnetic field. So James Clerk Maxwell also he unified the laws of electricity and magnetism, and that are called Maxwell equations. Okay, I gave you some amount of idea in the chapter magnetism and matter and moving charges and magnetism about Maxwell equations. Okay, now we are going to discuss these equations in detail. So Maxwell argued that this is indeed the case, not only electric current but also a time varying electric field generates the magnetic field. Means he inferred, he indicated the notion that reverse effect also exists. Okay, Maxwell work unified the domains of electricity, magnetism, and light, showing that light is an electromagnetic wave. So he unified all the laws of electricity and magnetism, and he proved that light is an electromagnetic wave. Okay, he gave four equations, Maxwell equations. Okay, and conclusion of these equations were that time varying magnetic field can produce electric field time varying electric field can produce magnetic field, and then he proved that light is an electromagnetic wave in which both time varying electric field and time varying magnetic field exist. Okay, electromagnetic waves are coupled time varying electric and magnetic fields that propagate in space. So electromagnetic waves, you may have studied a little bit in chemistry. Okay, so what are electromagnetic waves? They are coupled time varying electric and magnetic field. You may have studied it in waves chapter of 11th somewhat. You may have given a small idea about electromagnetic waves. Okay, so what are electromagnetic waves? They consist of both electric and magnetic field that are time varying. Both field and magnetic field are time varying fields. Okay, and both are mutually perpendicular to each other and perpendicular to the direction of propagation. So speed of EM waves according to Maxwell equation turned out to be very close to the speed of light. Okay, he calculated the speed through various experiments, and speed of electromagnetic waves according to Maxwell equations, it turned out to be very close to 3 newtons per 8 meter per second. That was speed of light obtained from optical measurements. So he done optical measurements. So he has done some experiments, due to which concluded he calculated that speed of EMF waves is approximately or very close to the speed of light in vacuum, that is 3 into 10 by 8 meter per second. Okay, so what is the problem in Ampere circuital law? He modified the Ampere circuital law. So what was the problem in Ampere circuital law? We will see. So fundamental laws of electricity and magnetism we rely on are, so what are the fundamental laws in magnetism and electricity? That is Gauss law for electricity, that is closed integral of electric field E dot dA. Closed integral over a closed surface of E dot dA is equal to Q upon epsilon naught. That is a statement of Gauss law for electricity. Okay, so closed integral over a closed surface, or we can say integral over a closed surface of E dot dA is equal to Q upon epsilon naught. That means magnetic flux, electric flux through any closed surface is equal to 1 by epsilon naught times the charge enclosed by that surface. That is a statement of Gauss law for electricity. Another law, Gauss law for magnetism, we have discussed, that is closed integral over closed surface B dot dA. That is called magnetic flux through any closed surface is always equal to 0. That means magnetic monopoles do not exist. Okay, magnetic field lines form closed loop, due to which outward flux equal to inward flux. That's why net flux through any closed surface is always 0. Net magnetic flux. That was Gauss law for magnetism. Now Faraday's law. What was Faraday's law? EMF epsilon is equal to d phi b upon dt. That was Gauss law. EMF is, we can say, a type of voltage, and we know the relation between electric field and potential difference and electric field. So E is equal to minus dV by dr. So potential difference is somewhat EMF. Okay, they both can be used interchangeably. So E is equal to minus dV by dr or dl. So minus dV will be equal to E dot dl, or we can say dV is equal to minus E dot dl, or closed integral. Okay, so here there was potential difference or EMF. In place of that, we have written minus closed integral E dot dl, and minus will go in right hand side. So Faraday law, another form of Faraday law is close integral over a closed loop E dot dl is equal to minus d phi b upon dt. One form is magnetic EMF induced is equal to magnitude of EMF induced is equal to rate of change of magnetic flux. That is one form. And another form, after putting EMF is equal to minus E dot dl close integral. Okay, according to the relation of electric field and potential difference. So close integral E dot dl is equal to minus d phi b upon dt. That is the another form of Faraday's law. This is third equation. And another Ampere circuital law. Close integral over closed loop B dot dl is equal to mu naught upon mu naught I. So what was the statement? That integral over a closed loop of magnetic B dot dl is equal to mu naught times the current passing through that loop. Okay, that was a statement of Ampere circuital law. Okay, so close integral of B dot dl is equal to mu naught times the current passing through that loop, or current enclosed by that loop. Okay, so that is the statement of Ampere circuital. So these are the four basic fundamental laws of electricity and magnetism on which we rely on in the entire chapter. So what was the problem with Ampere circuital law? We are going to discuss in detail. In certain situation, Maxwell identified a logical inconsistency in Ampere circuital law. So he identified something, some discrepancy, something missing in the Ampere circuital law. Okay, so Ampere's law violates the principle of charge conservation in the charging capacitor. Okay, we know we are going to discuss it, that how Ampere's law violates the principle of charge conservation in the charging capacitor in the upcoming slides. Okay, for now I am just saying that if we capacitor is connected to a source, okay, and current is flowing through the wire, and due to current flowing through the wire, magnetic field is being produced around the wire in the form of concentric circles. But when it reaches the plate of the one plate of the capacitor, and after that there is a space between the two plates of the capacitor, okay, inside that space there is a magnetic field, but there is no current. How that magnetic field is coming? Okay, he performed a experiment. He placed a magnetic needle near the wire, okay, a wire that is connecting the two plates of capacitor with the source. So he placed a magnetic needle near a wire. So that magnetic needle was showing the deflection. But when he placed that needle between the plates of the capacitor, it also shows the deflection. But there is no current flowing between the plates of the capacitor. Then how magnetic field is being produced between the plates of capacitor? So Ampere's law violated the principle of charge conservation in charging capacitors. Okay, and by this experiment, Maxwell identified a logical inconsistency in Ampere circuital law, that it is not completely correct. Okay, he argued that an electrical current in wire produces a magnetic field around it. Okay, this is true. Electrical current in wire produces magnetic field around it. But for logical consistency, a changing electric field between the plates of capacitor must also produce a magnetic field. So there was a deflection of needle when it is placed inside the plates of the capacitor. So for logical consistency, a changing electric field between the plates of means what is between the plates of the capacitor? There is electric field. Okay. So if we are changing this electric field, it must produce the magnetic field, due to which needle is showing the deflection. So this was his idea. Then he performed the experiment, or given a theoretical explanation also, and modified the Ampere circuital law. Okay, so to remove the logical inconsistency, Maxwell modified Ampere's law and formulated a set of equations involving electrical and magnetic fields and their sources, the charges and current densities. Okay, so he formulated a set of equations. The set of equations we have discussed in the previous slide. Only he modified the Ampere circuital law. Okay, other three equations were remained as it is, and these were, he unified these all the equations and formed a set of equation known as Maxwell equations. Okay, so and formulated a set of equations that involve electric and magnetic fields, their sources, and the charge and current densities. Okay, these equations are known as Maxwell equations. So first equation was that integral over closed surface E dot dl E dot dA equal to Q by epsilon naught. That was Gauss law for electricity. Okay, another equation, in integral over closed surface B dot dA equal to 0, means magnetic flux through any closed surface is always 0. Gauss law for magnetism. Okay, third equation, integral over closed loop E dot dl is equal to minus d phi b upon dt. That is Faraday's law, another form of Faraday's law. And he modified the Ampere's law, and the final law, modified law, is known as Ampere-Maxwell law. Okay, so closed integral over a closed loop B dot dl is equal to mu naught IC. This was the initial result for this B dot dl, mu naught IC only. IC is the conduction current that is flowing through the wire. Plus, what Maxwell added in the Ampere's law, he added mu naught epsilon naught d phi e upon dt. That term he added extra, and that term is due to the magnetic field present between the plates of the capacitor. Got it? That is known as Ampere-Maxwell law. So we will discuss how this term came into this expression and what is this term in detail. Okay, only here only this expression is written to infer you that this is Maxwell equation. Maxwell modified this equation, but what is this term we will discuss in further slides in detail. Okay, now in Ampere-Maxwell law or modified Ampere law, we can say it Ampere-Maxwell law or modified Ampere's law. Okay, B integral over closed loop B dot dl is equal to mu naught IC plus mu naught epsilon naught d phi e upon dt. That phi is electrical flux, not magnetical flux. Okay, so ID is equal to, this is known as displacement current. This term epsilon naught d phi upon dt is known as displacement current. Okay, that IC is called conduction current. Conduction current is flowing through the wire. Displacement current is that exists, that is hypothetical term. Okay, there is no displacement current. It is hypothetical term which is used so that we can bring consistency in the Ampere's law. Okay, so this term epsilon naught d phi e upon dt is known as displacement current. ID is equal to epsilon naught d phi e upon dt is known as displacement current. Okay, in the upcoming section, let us discuss the displacement current and its consequences. Okay, so what was the inconsistency in Ampere's law? Okay, so figure 8.A1a, a loop of radius r. So this is the parallel plate capacitor, and its plates are connected to a source which is providing time varying current, not fixed current. Time varying current is flowing through the wires that are connecting the capacitor. That's why it is written IT, means current is varying with time. So a loop of radius r, we are considering a loop of radius r to determine the magnetic field at point P on the loop. So outside the plates of the capacitor, we are considering a loop of radius r to find the magnetic field at P point. Okay, consider the process of charging a parallel plate capacitor C with a time dependent current. This is IT's time dependent current. It is varying with time, that is shown in the figure 8.1a. So we are consider a charged capacitor, a capacitor having parallel plates, and it is being charged by a current IT. So what is case 1? So in case 1, we are considering a flat circular surface S1. So this is L is loop, and surface enclosed by that loop is flat surface enclosed by that loop is S1. Okay, bounded by the loop L, and current IT passes through the, so that current IT is passing through that loop or surface. To find the magnetic field at point P, so to find the magnetic field at point P in figure 8.1a, let's apply Ampere circuit law. So what is ampere circuit law? B dot dl is equal to mu naught current flowing through that loop. Okay, so close integral B dot dl. So magnetic field along this loop will be equal to, or at this point P will be equal to, we can say it, close integral B, that B is magnetic field at this point P dot dl. That is the small element we have taken. We have seen the expression or derivation of ampere circuit law in that chapter. Okay, so B dot dl, so small element, due to small element, or at this element, small element, okay, is equal to mu naught I current enclosed by that loop. So what is the current enclosed by that loop? IT. Okay, so let's apply ampere circuit law to loop L just placed outside the capacitor. So integral over closed loop B dot dl is equal to mu naught, according to ampere circuit law, mu naught IT. So this is the current that is varying and flowing through this surface. NCERT equation 8.1. So inconsistency in ampere circuit law. So what was the inconsistency in ampere circuit law? So according to ampere circuit law, close integral B dot dl is equal to mu naught IT. So from symmetry, the magnetic field is directed along the circumference of the circular loop. So we know that magnetic field around a straight wire is in the form of concentric circles. So we have taken the loop of radius r. So magnetic field at this P point will be along this loop. Okay, due to the symmetry of the loop. So from symmetry, the magnetic field is directed along the circumference of the circular loop. Okay, it is same in the magnitude at all points on the loop. So it is same magnitude, direction of magnetic field at all points will be different, but magnitude, because at same distance, because P, we can take any point on this loop, it will be at same distance from the wire, that is r. Okay, due to which magnitude of magnetic field around this loop, along this loop, is same at all points. Okay, that is, so if we are doing this integration, so B and dl, so we will do the integration of this dl, so it will become L. So B into L, it is 2 pi r. L is 2 pi r. What is the perimeter of this circumference? 2 pi r. So we have B into 2 pi r equal to mu naught IT. NCERT equation 8.2. Okay, so we have reached here. So B is, at any instant B is constant, and dl, we are doing the integration of dl over a closed loop. It will came out to be perimeter of the circle, because it is circular loop. So 2 pi r. Okay, now figure 8.A, B and C. So what these figures are showing? So they are showing a closed loop again, but the surface enclosed by that loop is different. Okay, now B and C are showing a port shaped surface passing through the interior between the capacitor plates. So it is like pot, or it is like tiffin box. Okay, so means this is the opening of the pot. This L loop is opening of pot, or this is the surface of the pot, closed surface of the pot. Okay, so this pot is placed like somewhat like this, that closed opening is outward from the capacitor plates, and this surface or bottom of this pot is placed inside the space between the capacitor plates. Okay, but this surface is not touching anywhere on the current. Got it? Now B and C showing a pot shaped surface passing through the interior between the capacitor plates with loop L and its rim. So this is the rim of the pot, or we can say opening of the pot. Okay, this is like tiffin box. This is opening of tiffin box. Both these diagrams are representing same thing. Okay, a flat circular bottom. So this is flat circular bottom. Okay, S2. In this case, this is the flat bottom circular flat bottom circular bottom, and this is flat circular bottom in this case. Okay, so this is called S2 between the capacitor plate. So its bottom surface is placed inside the capacitor plate, its opening is outside the capacitor plates, where arrows indicates the uniform electric field between the plates. So these arrows are representing the uniform electric field from positive plate to negative plate. Okay, you can see. Now what is the case 2? Case 2 is this. Now consider a pot shaped open surface S2. This S2 open, this open surface, it is open from one mouth, one side. Okay, with the same boundary L. Boundary we are not changing. In the first case we have taken this loop, and surface we have taken flat surface enclosed by this loop. Now we have not taken flat surface, we have taken pot shaped surface whose bottom is lying between the plates of the capacitor. Okay, now consider a pot shaped open surface S2 with the same boundary L, rim of the pot. This is rim of the pot. Now surface of the pot passes between the capacitor plates and its bottom is flat. Its bottom is flat, and the bottom surface is passing between the, or it is lying between the plates of the capacitor. No conduction current passes through the surface S2. Now you can see conduction current is entering this loop, but the surface enclosed by this loop is like a pot, but current is terminating here at this positive plate. Okay, beyond this positive plate, between this positive and negative plate, there is no current, there is no conduction current. So current is not passing through that flat bottom surface. That means current is not passing through area enclosed by that loop. Okay, so no conduction current passes through the surface S2. That means if there is no current passing through the surface enclosed by this opening, that means closed integral B dot dl will be equal to mu naught I enclosed by this loop, or current passes through the area enclosed by that loop is 0. So B dot dl closed integral for this surface S2 will be equal to 0. This is contradiction. Now this contradicts the previous result. According to previous result, this loop is same, but the area enclosed was flat and the current was passing through that, and B dot dl closed integral was mu naught I. But in this case we have changed the surface enclosed by this loop. Loop is same, but now no current is passing through that surface, that pot surface, bottom surface of pot. That means B dot dl closed integral is equal to 0. That is contradiction. Line integral B dot dl cannot be both mu naught I in first case and 0 for same loops. If we are taking same loops in both cases, so closed integral B dot dl cannot have both the values mu naught I and 0. So this is contradiction. There is something missing in the Ampere's law. Okay, so contradiction between the values of B dot dl implies Ampere circular law is incomplete. Okay, so two values by taking two surfaces represent the incompletion of Ampere circular law, or inconsistency in the Ampere circular law. Since the contradiction arises from our use of Ampere circular law, this law must be missing something. Okay, the missing term must be such that one gets the same magnetic field at point P no matter what surface is used. Okay, so that missing surface should be such that if we are taking another surface, like we have taken pot surface or tiffin box surface, okay, in the second case, so result should be same, mu naught I. That type of missing term we have to put here, that Maxwell concluded or derived by experiments. Okay, so missing term must be such that one gets the same magnetic field. One must guess the B dl closed integral equal to mu naught I. Okay, doesn't matter what surface is being used, it is pot shaped or flat surface. Okay, one thing that we are missing here is the changing electric field. So how this missing term we can conclude, how this magnetic field between the capacitor plates is being produced. So what is we are missing here? We are missing because current is changing with time, due to which charge on the capacitor is changing with time, due to which electric field between the plates of the capacitor is changing with time. Because if charge on the capacitor is changing with time, electric field will eventually change with time. Okay, electric field depends on the charge on the plates. Okay, so if charge on the plates is changing due to the current change in current, So electric field between the plates of the capacitor will also change. For steady current, we know that electric field between the plates of the capacitor is constant. But for changing current, electric field between the capacitor will be time varying. Okay, due to which magnetic field is being generated. And we have to derive or conclude that missing term according to that concept of changing electric field. Okay, so that displacement current is hypothetical term. It is not actually a current, but a missing term that is named as displacement current. Okay, so Maxwell solved this inconsistency by postulating that time varying electric field is also a source of magnetic field. Okay, so he gave postulate that time varying electric field, that is the electric field that is varying with between the plates of the capacitor, is a source of magnetic field. How it is a source of magnetic field, we are going to see. Okay, now you can see another diagram, figure 8.2a, the electric and magnetic field E and B between the capacitor plates at point M. So there is a M point. So magnetic needle is placed here, due to which it is showing deflection, and magnetic field direction is shown by this arrow B. Okay, at this P point, again magnetic needle is showing same deflection. That means there is a current IT, due to which magnetic field is being produced, but here there is no current. So how this magnetic field is being produced? So this is a reverse effect, that changing magnetic field can induce the EMF or produce electric okay, similarly changing electric field can produce the magnetic field. Okay, from this thing Maxwell got an idea. Okay, while the capacitor is charging, the electric field E between the plates changes with time because current is time dependent. Okay, current is time dependent, due to which charge on the capacitor, charge accumulated on the plates of the capacitor is also changing with time, due to which electric field depends on the charge on the capacitor. So electric field is also varying with time, that exists between the plates of the capacitor. So time varying electric field generates a magnetic field. He introduced the concept of a new type of current that is called displacement current, but it is not actually a current. It is a missing term that is named displacement current to bring the consistency in the Ampere circuit law. Okay, which flows as long as the electric field is changing between the plates of the capacitor. Okay, till current is varying. Okay, as long as current is varying, as long as electric field is changing between the capacitor plates, that displacement current will exist between the plates of the capacitor. Okay, when the electric field between the plates of the capacitor become constant, then this displacement current disappears and there is no magnetic field between the plates of the capacitor. Okay, only changing magnetic field, or we can say changing electric field, will produce the magnetic field. Now electric flux phi E between the plates, let S be the surface, let S be the surface area of plates and Q be the charge. So electric field between the plates of the capacitor is given by, we have discussed what is the electric field between the plates of the capacitor in electrostatic potential and capacitance chapter also. So that is expression for electric field is sigma by epsilon naught. Sigma is surface charge density, that is Q upon area, charge upon area. So sigma by epsilon, which is equal to Q is the charge on the plate, S is the area of the surface area of the plates. So Q by S epsilon naught. This is the electric field that exists between plates of the capacitor at any time, at any instant. Okay, it is changing at any instant, its value is this. So figure 8.8, see a cross sectional view of figure A. So electric flux through surface S is, so phi E is equal to E dot S. So this is the magnetic, or this is the electric flux through the surface S, that surface. So electric field is passing through that surface. So electric flux through this surface, because this surface is placed exactly perpendicular to, or we can say exactly along the plates of the capacitor, or exactly perpendicular to the electric field. That's why E dot S will become ES cos 90 degree. Cos 90 degrees, sorry, E dot S ES cos 0 degree, because angle between this electric field and area vector. What is the area vector of this surface? It is perpendicular to this surface. So perpendicular to this surface means along the electric field. So theta is 0 degree. So ES cos 0 degree, which is cos 0 degree is 1. So E dot DS will become, sorry, E dot S will become ES cos 0 degree, which will become ES. Okay. So E is Q by S epsilon naught. So Q by S epsilon naught into S. So S and S will get cancelled out. So electric flux through the surface S will become Q by epsilon naught. And this is NCERT equation 8.3. So electric flux is equal to Q by epsilon naught. We have discussed. Now, this is also according to Gauss law. Electric flux through any closed surface will be equal to 1 by epsilon naught times the charge enclosed by that surface. Now, differentiating the flux equation with respect to time. So, d phi E. Now, differentiating this equation on both sides with respect to t, with respect to time. So, d phi E upon dt will be equal to epsilon naught is constant. So, 1 by epsilon naught dq by dt. So, this q is not constant because charge is accumulated and it is increasing. This current is increasing, charge on the capacitor is increasing with respect to time. So, dq by dt. Okay. Now, epsilon naught, you can bring or shift this epsilon naught on the left hand side. So, epsilon naught d phi E upon dt will become equal to dq by dt. This dq by dt is equal to current. Okay. So, that's why we called it displacement current. Okay. Because it comes epsilon naught d phi E upon dt is equal to dq by dt, and dq by dt we know what is dq by dt, rate of change of charge flowing through a conductor. Okay, between the plates there is no charge flowing from one plate to another plate. Okay, but according to theoretical derivation it came out to be dq by dt, which is rate of change of charge flowing. Okay, so since I is equal to dq by dt, current is equal to dq by dt, so we can say that term epsilon naught. So we can say, it is not exactly, so we can say term epsilon naught d phi E upon dt has the dimension of current. So this whole term has the dimension of current. That's why it is called displacement current. It is named a current, that is displacement current. Okay, so I is equal to, we can write dq by dt as I equal to epsilon naught d phi E upon dt, NCERT equation 8.4. Now I equal to epsilon naught d phi E upon dt. This is the missing term in Ampere circuital law. Okay. Now, current carried by conductors due to flow of charges is called conduction current. Okay. Charges are flowing in the wire. Due to the flow of charges in the wire, the current carried by the conductors. Okay. Due to the flow of charges, that's why it's called conduction current. So that normal current we have discussed that is flowing through the wires is known as conduction current. Okay. Also from equation 8.4, I is equal to epsilon naught d phi E upon dt. So this current is called displacement current. Current given in equation 8.4 is a new term and is due to the changing electric field or electrical displacement, an old term still sometimes used. It is known as electrical or electric displacement also. That was an old term. New term is displacement current. Okay, it is therefore called displacement current or Maxwell's displacement current. So displacement, it is represented by ID. Conduction current is represented by IC. So displacement current ID is equal to epsilon naught d phi E upon dt. Displacement current exists wherever the electric field is changing with time. Okay, when electric field is changing with time, that displacement current will exist there. Maxwell made generalization that source of magnetic field is not just the conduction electric current due to flowing charges but also the time rate change of electric field. Okay, so what Maxwell generalized, that source of magnetic field is not just the conduction electric current due to flowing charges but also the time rate of change of electric field produce the magnetic field. Okay, So he generalized that magnetic field cannot only be produced by conduction current, but magnetic field can be due to the time varying electric field also. Okay, so he modified Ampere's law by adding displacement current to the conduction current. Okay, so total current I now becomes, in the equation he modified that total current is equal to, that total enclosed current will be equal to I, that is equal to IC plus ID. Okay, conduction current plus displacement current, that is equal to IC plus epsilon naught d phi e upon dt. What was ID? We have discussed epsilon naught d phi e upon dt, that is NCERT equations 8.5, that is total current. Okay, Ampere's law become Ampere's modified law, or called Ampere's Maxwell law. That is, now this is the modified law. Closed integral B dot dl is equal to mu naught in the beginning. Okay, Ampere's circular law was closed integral B dot dl equal to mu naught I only. Now Maxwell modified it. In the place of I, he wrote IC plus ID, conduction current plus displacement current. So after putting the values of conduction current and displacement current, B dot dl over closed loop is equal to mu naught IC plus mu naught ID, and ID is epsilon naught d phi upon dt, NCERT equation 8.6. This is the complete expression for this is the modified Ampere's Maxwell law. Okay, again expression. Now Ampere's modified law is now logically consistent for all the cases. Now you can see outside the plates of the capacitor, this d phi e upon dt will be 0. Only mu naught IC will be there outside the capacitor. Inside the capacitor, IC will be 0. So that term will be 0. Only mu naught epsilon naught d phi upon dt will be there. So between the plates of the capacitor and outside the plates of capacitor, B dot dl over closed integral will never be 0. Okay, so now this law is logically consistent for all the cases. So this means that outside the capacitor plates, surface S1, we have only conduction current IC equal to I and ID equal to 0. Okay, and B dot dl will be equal to mu naught IC outside the capacitor plates. But inside the capacitor plates, on the other hand, inside the capacitor plate for surface S2, IC is 0, conduction current is not there inside the plates of capacitor, but ID exists due to rate of change of magnetic flux with time. So ID will be equal to epsilon naught d phi upon dt, which is equal to I. So close integral B dot dl will be equal to mu naught ID. Okay, thus Ampere's Maxwell law gives same result for both S1 and S2 surface. And now this law is logically consistent for all the cases. Okay, in some cases, for example, steady electric fields in a conducting wire, the displacement current may be 0. Okay, since the electric field E does not change with time. So when there is a steady electric field, I have mentioned already that if there is a steady electric field in a conducting wire, displacement current may be 0, since the electric field does not change with time. If electric field is not changing with time, then rate of change of magnetic flux with respect to time will be 0. So there will be no displacement current. Okay, in other cases, for example, the charging capacitor, both conduction and displacement current may be present in the different regions of space. Okay, in other cases, that case we have discussed, if current is changing in the circuit or across the capacitor, due to which charge on the plates of the capacitor will change, and electric field that exists between the plates of the capacitor will change, due to which magnetic field is produced and displacement current will be there. Okay, so in other cases, for example, the charging capacitor is charging, it is not charged fully. Both conduction and displacement current may be present in the different regions of space. Got it? Once the capacitor is fully charged, it will block the current. Okay, then there will be no conduction current, no displacement current. So result will be same. Close integral B dot dl will be same for charging capacitor or for fully charged capacitor. In most of the cases, they both may be present in the same region of space. Okay, in most of the cases, both conduction and displacement can be present on both in the same region of space. Like if we are inserting some dielectric material between the plates of the capacitor. Okay, so there will not be conduction current, but no dielectric is perfectly insulating. Okay, some amount of current, very small amount of current may be flowing through that dielectric also. Okay, due to which conduction, very small amount of conduction current will be there, but large proportion of displacement current will be there. Okay, so we can say that no perfectly conducting or perfectly insulating medium is there. That's why both conduction and displacement current can exist in the same region of space also. Okay, so most interestingly, there may be large regions of space where there is no conduction current, but there is only a displacement current due to time varying electric field. Okay, some space regions of space may exist in which there is no conduction current, only time varying electric fields are there. Okay, in the case of electromagnetic waves also, only time varying electric field is there. Okay, due to which magnetic field will be there. Okay, due to which displacement current will be there. Okay, so some regions of space can exist in which there is no conduction current but only displacement current due to time varying electric field. Prediction of such displacement current can be verified experimentally. So we can verify this. So again the diagram 8.2a, which is electric and magnetic fields E and B between the capacitor plates at point M and B. That B diagram is cross sectional view of figure A. So figure A, the cross sectional view of figure A is shown in the figure B. Okay, when we are viewing this capacitor from one side. So plates of the capacitor are circular, not rectangular. Okay, that's why the cross sectional view is two circles. Okay, so this is the magnetic field. This is the loop we have taken outside the capacitor plates of radius r. So magnetic field on this loop will be like this, as shown in the figure. This cross are not magnetic field. Okay, magnetic field is in the plane, and this capital R is radius of the capacitor plate. Okay, this cross is electric field that is existing from positive plate to negative plate, and we are viewing from one side of the capacitor plate. So this cross is electric field direction. Okay, for example, a magnetic field, say at point M between the plates of capacitor in figure 8.2a, can be measured and is seen to be same as just outside at P. So magnetic field at point M and P will be same. Okay, as shown in the figure. So we can say that time dependent electric field and magnetic field give rise to each other. Okay, so time dependent electric field produce magnetic field, time dependent magnetic field produce electric field. Faraday law of electromagnetic induction and Ampere Maxwell law gives a quantitative expression of this statement, with the current being the total current as in the equation 8.5. So we have discussed in equation 8.5 what is total current, sum of conduction and displacement current. Okay, so Faraday law of electromagnetic induction and Ampere's Maxwell law give a quantitative expression for this statement, that time dependent electric field produce magnetic field and magnetic time dependent magnetic field produces electric field. Okay, one very important consequence of this symmetry is the existence of electromagnetic waves, which we will discuss in next lecture. Okay, so due to this due to this conclusion, Maxwell concluded that light is an electromagnetic wave. Okay, so due to this discovery that time varying electric field can produce magnetic field and time varying magnetic field can produce electric field, and they are interrelated. By this idea, he proceeded with this idea and discovered that light is an electromagnetic wave. Okay, so Maxwell equations are a set of four fundamental equations that form the foundation of classical electromagnetism, optics, and electric circuit. So there are four Maxwell equations. So first is Gauss law for electricity. So this is the first equation of Maxwell. He unified the equation that is given by Gauss, but he unified the equation. That's why it is called Maxwell's equation. Okay, so close integral E dot dI is equal to Q by epsilon naught. What that equation means Meaning is electric flux through a closed surface is proportional to the net charge enclosed. It relates electric field to its charge source. Another Gauss law for magnetism, second equation, that is closed integral B dot dA is equal to 0. That means magnetic flux through any closed surface is always 0. This implies the magnetic monopoles do not exist. Third equation is Faraday law of induction, that is closed integral E dot dl equal to minus d phi B upon dt. Meaning of this equation is, significance of this equation is, a changing magnetic flux induces an electromotive force and hence an electric field. Ampere's Maxwell law. This is the law in which Maxwell had done some modifications. So closed integral B dot dl is equal to mu naught IC, that is conduction current, plus mu naught epsilon naught d phi E upon dt. Okay, so meaning magnetic field is produced by both conduction current and a changing electric flux, that is by the displacement current. So there is a summary. Displacement current is given by ID is equal to epsilon naught d phi E upon dt. Okay, total current is equal to conduction current plus displacement current. Maxwell equation unify electricity and magnetism. Time varying electric field produces magnetic fields. Important formulae: Ampere Maxwell law, closed integral B dot dl is equal to mu naught IC plus ID, where ID is equal to epsilon naught d phi E upon dt. Okay, practice. There are some practice questions. For a parallel plate capacitor being charged, if the rate of change of charge is 3 ampere and area of plates is 0.02 meter square, calculate the displacement current, the rate of change of electric field between the plates. Given epsilon naught is equal to 8.85 into 10 power minus 12 coulomb square per Newton meter square. Second question is, electric flux through the space between the plates is changing at a rate of 100 Weber per second. Calculate the displacement current. For a charging capacitor, if IC, conduction current, represents the conduction current through the connecting wire and ID represent the displacement current between the plates, then IC is equal to ID, IC greater than ID, IC less than ID, or IC and ID are unrelated. Okay, so these are some practice questions you have to do yourself. So this is all about introduction and displacement current of chapter electromagnetic waves. So I hope you enjoyed the session. Thank you, but don't go anywhere. We have to do the DPP. So open your DPP in your Sathee app. Okay. First question, which term in the Ampere Maxwell law accounts for the magnetic field between the plates of charging capacitor? Conduction current, displacement current, both conduction and displacement, none of the above. So you can write your options in or write your answers in comment section. So which term in the Ampere Maxwell law? What is the expression for displacement current in terms of electric flux phi E? ID is equal to epsilon naught d phi E upon dt, or ID is equal to mu naught d phi E upon dt, or ID is equal to d phi E upon dt, ID is equal to 1 by epsilon naught d phi E upon dt. Which expression is correct for displacement current? In the Ampere Maxwell law, the term mu naught epsilon naught d phi E upon dt represent conduction current density, displacement current contribution, magnetic flux, or electric field intensity. Which surface in the capacitor setup would have zero conduction current but non-zero displacement current? Surface enclosing one plate of the capacitor, surface passing through the wire outside the capacitor, surface between the capacitor plates, surface enclosing the entire capacitor. Which symmetry correction did Maxwell introduce to Ampere's law, including conduction current only, adding displacement current to conduction current, removing conduction current, or introducing magnetic monopoles? Yes. Okay. So this is DPP section. So make sure you solve the DPP in the lecture or after the lecture. So this is all about today's lecture. Thank you.